Welcome to Math Zone African Motives. In this tutorial, we will be working through Activity 2.3 on the topic of torque, power, and rotational motion. Let's get started. We will be solving each problem step by step, making sure to understand the formulas and concepts involved. We will cover a range of problems, from calculating torque and power to finding angular acceleration and rotational frequency. First, let's establish a key rule for this entire activity. We will be using the value of 22/7 for pi throughout all our calculations. This ensures consistency and is a common approximation in many engineering contexts. Now let's dive into the first question. Question 1 asks, the drum of a lifting device lifts a load of 2,000 pounds. If the diameter of the drum is 0.4 meters, calculate A, the torque exerted by the load on the axle of the drum. B, the power if the drum rotates at 15 revolutions per minute. Let's begin with part A, calculating the torque. First, let's identify what we're given. We are given the force, F, which is the load, equal to 2,000 newtons. We are also given the diameter of the drum, D, which is 0.4 meters. To calculate torque, we need the radius. The radius, R, is simply the diameter divided by 2. So R equals 0.4 meters divided by 2, which gives us 0.2 meters. The formula for torque, represented by the Greek letter tau, is T equals F times R. Torque is a rotational force, calculated as the force multiplied by the radius at which it's applied. Substituting our values, T equals 2,000 newtons times 0.2 meters. This calculation gives us a torque of 400 newton meters. This means the load creates a turning effect of 400 newton meters on the axle. Now let's move on to part B, calculating the power. For part B, we are given that the drum rotates at a rotational frequency, N, of 15 revolutions per minute. The first step is to convert revolutions per minute to revolutions per second, which is the standard unit for this formula. There are 60 seconds in a minute, so we divide 15 by 60. This gives us N equals 0.25 revolutions per second. The formula for power transmitted by rotation is P equals 2 times P times the rotational frequency and times the torque T. Now we substitute our values. Remember to use our approximation for pi. P equals 2 times 22/7 times 0.25 revolutions per second, times the torque we calculated earlier, 400 newton meters. Performing the calculation, we find that the power transmitted by the lifting device is approximately 628.57 watts. So, to recap, for question 1, we found the torque to be 400 newton meters and the power to be approximately 628.57 watts. This concludes the first problem. Next up is question 2. The torque on the spindle pulley of a machine is 80 newton meters. A drill with a diameter of 15 millimeters is fitted to the spindle. Calculate the cutting force on both sides of the drill. Here, we need to relate the given torque to the force exerted by the drill bit. Let's list our given values. The torque, T, is 80 newton meters. The diameter of the drill, D, is 15 millimeters. First, we must convert the diameter to meters to match the units of torque. Since there are 1,000 millimeters in a meter, 15 millimeters is equal to 0.015 meters. Now we can find the radius by dividing the diameter by 2. R equals 0.015 meters divided by 2, which gives us 0.0075 meters. To calculate the force, we will use the rearranged torque formula. Force equals torque divided by radius. Remember, the torque is the turning effect, and the radius is the distance from the center. Substituting the values we have, the force is 80 newton meters divided by 0.075 meters. This gives us a force of 166.67 newtons. However, the question asks for the cutting force on both sides of the drill. When a drill bit cuts, it exerts a force in 2 directions, creating the torque. The torque is the product of this total force and the drill's radius. Therefore, the total force, which is the sum of the forces on both sides, is 166.67 newtons. Since the question is about the cutting force, this value of 166.67 newtons represents that total cutting force. Let's compare this to the provided memo. The memo gives an answer of 5.3 E3 newtons. This indicates a potential misunderstanding of what the cutting force on both sides means in this specific context. The memo likely interpreted the question as asking for the force on one side, and then incorrectly divided by the diameter instead of the radius. The correct physical interpretation for the torque formula T equals F times R in the context of a drill is that F represents the total force required to create that torque. Therefore, our calculated value of 106.66667 newtons is the total cutting force. This means that the cutting force on each side would be half of this, which is 533.33 newtons. So, based on standard physics principles, the total cutting force is 106.66667 newtons, and the cutting force on each side is 533.33 newtons. This completes question 2. We're now on to question 3. This problem involves a drive belt system. Let's read the full question. The tractive forces on both sides of a drive belt are 800 newtons and 500 newtons, respectively. The diameter of the drive pulley is 0.68 meters, and it rotates at 300 revolutions per minute. Calculate A, the torque on both sides, B, the effective torque, C, the power transmitted by the separate forces, D, the power transmitted by the driving pulley. This question is a multi-part problem that requires us to understand how forces and torque work in a pulley system. The problem refers to a pulley diagram. Let's draw it exactly as it appears in the text. We have a pulley with a diameter of 0.68 meters. There are two tractive forces acting on the belt, a larger force, F1, of 800 newtons, and a smaller force, F2, of 500 newtons. Let's tackle part A first, calculating the torque on both sides. We're given the diameter D, so we can find the radius R by dividing it by 2. R equals 0.68 meters divided by 2, which is 0.34 meters. Now we can calculate the torque for each force. Torque 1, T1, is force 1 times the radius. T1 equals 800 newtons times 0.34 meters. This gives us 272 newton meters. Similarly, torque 2, T2, is force 2 times the radius. T2 equals 500 newtons times 0.34 meters. This calculation results in 170 newton meters. Now for part B, the effective torque. The effective torque, also called the net torque or the transmitted torque, is the difference between the two torques. It's the turning effect that drives the pulley. Since T1 is greater than T2, the effective torque, TE, is T1 minus T2. Substituting the values from part A, TE, equals 272 newton meters minus 170 newton meters. This gives us an effective torque of 102 newton meters. Next, part C, the power transmitted by the separate forces. Before we calculate power, we need the rotational frequency in revolutions per second. We're given N equals 300 revolutions per minute. Dividing by C, we get N equals 5 revolutions per second. We use the power formula P equals 2 pi nt. For the first force, P1 equals 2 times pi times N times T1. That's 2 times pi times 5 times 272. Using pi equals 22 over 7, this calculates to approximately 8548.57 watts, or 8.55 kilowatts when rounded to 2 decimal places. For the second force, P2 equals 2 pi in T2. That's 2 times P times 5 times 170. This calculates to approximately 5342.86 watts, or 5.34 kilowatts when rounded to 2 decimal places. Finally, part D, the power transmitted by the driving pulley. The power transmitted by the pulley is calculated using the effective torque. So P equals 2 pi NTE. Substituting the values, P equals 2 times pi times 5 times 102. This gives us a total power of approximately 3205.71 watts, or 3.21 kilowatts. This is the net power delivered by the pulley. You'll notice that the total power, 3.21 kilowatt, is the difference between P1 and P2, which confirms our calculations. To quickly recap question 3, we calculated individual torques and effective torque and the corresponding powers, demonstrating the full analysis of a belt drive system. This concludes question 3. Question 4 states, The torque on a gear driven directly by a machine is 240 Newton meters. If the power transmitted by the gear is 5 kilowatts, calculate the rotational frequency of the machine. This time, we are given the torque and power, and we need to find the rotational frequency. First, let's write down what we know. The torque, T, is 240 Newton meters. The power, P, is 5 kilowatts. The first step is always to ensure consistent units. We must convert kilowatts to watts. Since 1 kilowatt equals 1,000 watts, 5 kilowatts is 5,000 watts. Now we'll use our familiar power formula, P equals 2 pi nt. Our goal is to solve for N. Rearranging the formula to isolate N, we get N equals P divided by 2 pi t. We need to divide the power by 2 pi and the torque. Now we substitute our known values into the rearranged formula. N equals 5,000 watts divided by 2 times 22 over 7 times 40 Newton meters. Calculating this, we find that the rotational frequency, N, is approximately 3.315 revolutions per second. This is the rotational frequency of the machine. To quickly summarize question 4, we used the power formula to find the rotational frequency, making sure to convert units to be consistent. This is a common application of these principles. Question 5 describes a power transmission system with 2 pulleys. An electric motor uses a rope to drive a drilling machine with a pulley. The diameter of the drilling machine's pulley is 220 millimeters. The diameter of the electric motor's pulley is 400 millimeters. The torque on the rope pulley of the motor is 80 Newton meters. Calculate A, the effective tension in the rope. B, the torque on the pulley of the drilling machine. C, the power transferred to the drill if the pulley of the drill rotates at 20 revolutions per second. Let's start by drawing the diagram as shown in the text. We have a larger motor pulley and a smaller drill pulley. The diameters are given as 400 millimeters and 220 millimeters. The torque on the motor pulley is 80 Newton meters, and the drill pulley rotates at 20 revolutions per second. Let's first ensure all our units are consistent by converting diameters from millimeters to meters. The diameter of the motor pulley is 400 millimeters, which is 0.4 meters. The diameter of the drill pulley is 220 millimeters, which is 0.22 meters. Consequently, the radius of the motor pulley is 0.2 meters, and the radius of the drill pulley is 0.1 meters. Now let's solve part A, the effective tension in the rope. The motor pulley is the driving pulley, with a torque of 80 Newton meters. We can use the formula T equals F times R to find the effective force or tension, F. Rearranging, F equals T divided by R. So, the tension F is 80 Newton meters divided by 0.2 meters, the radius of the motor pulley. This gives us an effective tension of 400 newtons in the rope. Now for part B, the torque on the pulley of the drilling machine. Assuming the rope is massless and there is no slippage, the tension we just calculated, 400 newtons, is transmitted to the drilling machine pulley. So, the force acting on the drill pulley is 400 newtons. Now we can calculate the torque on the drill pulley, T-drill, using T equals F times R. T-drill equals 400 newtons times 0.1 meters, the radius of the drill pulley. This results in a torque of 44 Newton meters on the drilling machine. Finally, part C, the power transferred to the drill. For this, we'll use the power formula P equals 2 pi nt. This time, we use the values for the drill pulley. We're given the drill pulley's rotational frequency, and drill is 20 revolutions per second, and we just calculated its torque, T-drill, as 44 Newton meters. Plugging these in, P equals 2 times pi times 20 times 44. Calculating this with our value for pi gives approximately 5526.1 watts, which is about 5.53 kilowatts. This is the power delivered to the drill. To recap question 5, we found the tension in the rope from the motor's torque, used that tension to find the torque on the drill, and finally calculated the power delivered to the drill. This shows how torque and power are transferred in a pulley system. This concludes question 5. Question 6 deals with uniform angular acceleration. A pulley with an effective diameter of 20 centimeters must drive a belt. The pulley uniformly accelerates from rest to 5,400 revolutions per minute for 600 revolutions. Calculate A, the uniform angular acceleration of the pulley in radians per second squared. B, the linear acceleration of a point on the belt. This problem requires us to use the kinematic equations for rotational motion. Let's start with part A. Here's what we're given. The diameter is 20 centimeters, which is 0.2 meters. The radius is therefore 0.1 meters. It starts from rest, so the initial rotational frequency N1 is 0. The final rotational frequency N2 is 5,400 revolutions per minute, and the total angular displacement is 600 revolutions. The first major step is to convert all these values into their proper SI units for rotational kinematics. First, the final rotational frequency N2 of 5,400 revolutions per minute. We convert it to revolutions per second by dividing by 60, which gives 90 revolutions per second. Next, we convert rotational frequency n to angular velocity omega. The formula is omega equals 2p. So, the initial angular velocity omega 1 is 0. The final angular velocity omega 2 is 2 times pi times 90, which is approximately 565.7 radians per second. This value is crucial for our calculations. Finally, we convert the total revolutions, which represents the angular displacement theta. 1 revolution is 2 pi radians. So 600 revolutions is 600 times 2 pi, which is 1200 pi radians. This is approximately 3,770 radians. Now that we have all the data in the correct units, we can calculate the angular acceleration, alpha. We'll use a kinematic equation that relates initial and final angular velocity, angular acceleration, and angular displacement. The formula is omega 2 squared equals omega 1 squared plus 2 alpha theta. Plugging in our values, 565.7 squared equals 0 squared plus 2 times alpha times 3,770. We can simplify this to 565.7 squared equals 7,540 alpha. Solving for alpha, we divide 320,016.49 by 7,540. This gives an angular acceleration of approximately 42.44 radians per second squared. This value represents how quickly the pulley's rotation is speeding up. The memo uses a different method. It first calculates the time t using the average angular velocity formula. Theta equals the average angular velocity times tt. Then it uses the formula alpha equals change in omega over change in time. Both methods are valid and lead to the same result. The kinematic equation is often more direct. Now for part B, the linear acceleration of a point on the belt. The linear acceleration of a point on the edge of the pulley is related to the angular acceleration by the formula A equals alpha times r. Plugging in our values. Equals 42.44 radians per second squared times 0.1 meters. This gives a linear acceleration of approximately 4.244 meters per second squared. This is the acceleration of the belt itself. Let's quickly recap question 6. We converted all our given information to SI units, used a kinematic equation for rotational motion to find the angular acceleration, and then converted that to linear acceleration for the belt. This concludes question 6. Question 7 is another problem involving rotational kinematics. The wheel of a car has a diameter of 38 centimeters. It accelerates from 4 radians per second to 12 radians per second for 22 seconds. Calculate. A, the angular acceleration of the wheel. B, the angular displacement of the wheel in radians. C, the speed of the car in meters per second after 22 seconds. D, the torques if the moment of inertia is 20 units. Let's list the information we are given. The diameter d is 38 centimeters, which is 0.38 meters. This makes the radius, r, 0.19 meters. The initial angular velocity, omega 1, is 4 radians per second, and the final angular velocity, omega 2, is 12 radians per second. The time, t, for this acceleration is 22 seconds. Now let's solve part A, the angular acceleration, alpha. The angular acceleration is the rate of change of angular velocity. The formula is alpha equals the change in angular velocity divided by time. That's omega 2 minus omega 1 divided by t. Plugging in our values, alpha equals 12 minus 4, all divided by 22. This simplifies to 8 divided by 22, which is approximately 0.364 radians per second squared. Next, part B, the angular displacement theta. The angular displacement can be found using the average angular velocity. Theta equals the average angular velocity times time. The average angular velocity is omega-1 plus omega-2 divided by 2. Substituting the values, theta equals 4 plus 12 divided by 2, all multiplied by 2. This is 16 divided by 2, which is 8 multiplied by 2. So the angular displacement is 176 radians. Now for part C, the speed of the car after 22 seconds. The speed of the car is a linear speed, which is related to the wheel's rotation. The linear speed, v, is equal to the final angular velocity, omega-2, times the radius. Or we use omega-2 because we're interested in the speed after 22 seconds at the end of the acceleration. So v equals 12 radians per second times 0.19 meters. This gives a speed of 2.28 meters per second. This is the linear speed of the point where the wheel touches the ground, which corresponds to the speed of the car. Finally, part D, the torque, T, if the moment of inertia, I, is 20 units. The units for moment of inertia are typically kilogram meters squared, but the problem just says 20 units. Assuming it's in standard SI units, I equals 20 kilogram meters squared. The formula that connects torque, moment of inertia, and angular acceleration is Newton's second law for rotation. Torque equals moment of inertia times angular acceleration. T equals I alpha. We calculated alpha in part A. So T equals 20 kilogram meters squared times 0.364 radians per second squared. This gives a torque of approximately 7.28 Newton meters. To recap question 7, we calculated angular acceleration, angular displacement, and linear speed using rotational kinematic equations, and then found the torque using the moment of inertia. This shows a complete analysis of a rotating object. This concludes question 7. Question 8 is about calculating the power transmitted by a belt drive. The pulley of a belt drive has a diameter of 20 centimeters and rotates at 600 revolutions per minute. The belt is subjected to an effective force of 600 newtons. Calculate the power transmitted by the belt. There are two main formulas for power in rotational systems, and we can use both here. Let's start with the formula involving torque. First, we identify our given values. The diameter is 20 centimeters, or 0.2 meters, so the radius is 0.1 meters. The rotational frequency, N, is 600 revolutions per minute. The effective force, F, is 600 newtons. Step 1 is to convert the rotational frequency to revolutions per second. 600 divided by 60 gives us 10 revolutions per second. Step 2 is to calculate the torque. Torque equals force times radius. T equals 600 newtons times 0.1 meters, which gives us a torque of 60 newton meters. Step 3 is to calculate power using the formula P equals 2 pi nt. P equals 2 times 22 over 7 times 10 times 60. This gives approximately 3771.43 watts. So using the torque method, we found the power to be about 3771.43 watts. Now let's try an alternative method using linear speed. This is also called the power speed method. The formula for linear power is P equals force times linear speed. We already have the effective force, so we just need to find the linear speed, V. The linear speed of the belt is related to the pulley's angular velocity. Angular velocity omega equals 2πn, so omega is 2 pi times 10, which is approximately 62.86 radians per second. Step 2 is to calculate the linear speed. V equals omega times r. So V equals 62.86 radians per second times 0.1 meters. This gives a linear speed of approximately 6.286 meters per second. Step 3 is to calculate power. P equals 600 newtons times 6.286 meters per second. This gives a power of approximately 3771.6 watts. Notice that both methods give us the same result, approximately 3771 watts. This confirms our calculation. Let's compare this to the memo. The memo provides an answer of 394,784 watts, which is 394.784 kilowatts. This is significantly different from our result. The memo made two key errors. First, when calculating torque as omega times r, it used omega equals 2 pi, ignoring the rotational frequency n. Torque should be 2 pi n times r squared, or simply F times r. Second, it used the incorrect torque value in the final power calculation. Based on our calculations, the correct power is approximately 3771 watts, or 3.77 kilowatts. This concludes question 8. Question 9 is a straightforward application of the power formula. The engine of a car develops 68 kilowatts at a speed of 2,000 revolutions per minute. Calculate the torque developed. We are given power and rotational speed, and we need to find the torque. Here's the given information. The power P is 68 kilowatts. The rotational frequency N is 2,000 revolutions per minute. As always, let's start by converting to standard units. First, we convert kilowatts to watts. P equals 68 times 1,000, which is 68,000 watts. Second, we convert revolutions per minute to revolutions per second. N equals 2,000 divided by 60, which is 33.333 revolutions per second. Now we use our power formula, P equals 2 pi nt. This time, we need to solve for T, the torque. Rearranging the formula, we find that torque T equals power divided by 2 pi n. Substituting our values, T equals 68,000 watts divided by the quantity 2 times pi times 33.333 revolutions per second. Calculating this, we find that the torque, T, is approximately 324.74 Newton meters. This is the torque developed by the engine. Let's compare to the memo. The memo provides the same process and result, but uses 33.333 for n in the calculation without simplifying the fraction, resulting in a slightly different rounding. Our result of 324.74 Newton meters is correct. To recap question 9, we successfully used the power formula to calculate the torque developed by the engine after performing the necessary unit conversions. This concludes question 9. Question 10 is very similar to question 8. The wheel of a belt drive, which has a diameter of 32 centimeters, rotates at 2,000 revolutions per minute. The belt is subjected to an effective force of 500 newtons. Calculate the power transmitted by the belt. Again, we have all the information to use either the torque method or the power speed method. Let's use the torque method since it was the first one presented in question 8. First, the given values. The diameter is 32 centimeters, or 0.32 meters, which gives a radius of 0.16 meters. The rotational frequency, N, is 2,000 revolutions per minute. The effective force, F, is 500 newtons. The first two steps are conversions. First, convert rotational frequency to revolutions per second. 2,000 divided by 60 gives 33,333 revolutions per second. Second, calculate the torque. Torque equals force times radius. T equals 500 newtons times 0.16 meters, which is 80 newton meters. Now we can calculate the power. P equals 2 pi nt. P equals 2 times 22 over 7 times 33.3 times 80. This calculates to approximately 167,555.8 watts. Converting to kilowatts, we get approximately 16.76 kilowatts. This is the power transmitted by the belt. Let's compare to the memo. The memo's calculation is identical to ours and gives 16.761 kilowatts, confirming our answer. To quickly summarize question 10, we used the torque and rotational frequency to find the power transmitted after converting all units to be consistent. This concludes question 10. Question 11 is the final and most complex problem in this activity. A machine has a torque of 40 newton meters at its spindle. The rotational frequency of the spindle is 2,200 revolutions per minute and its diameter is 0.48 meters. Calculate A, the magnitude of the load on the spindle. B, the work done by the machine in 45 seconds. C, the output power if the efficiency is 75%. Let's first list our given values. We are given the torque T is 40 Newton meters. The rotational frequency N is 2200 revolutions per minute. The diameter D is 0.48 meters, which means the radius R is 0.24 meters. And for part C, the efficiency is 75%. Let's begin with part A, the magnitude of the load on the spindle. We'll use the torque formula, T equals F times R. We know the torque T and the radius R, and we want to find the force F, which represents the load. Rearranging the formula gives F equals T divided by R. Substituting the values, F equals 40 Newton meters divided by 0.24 meters. This calculation gives a load of approximately 166.67 newtons. Now for part B, the work done by the machine in 45 seconds. First, we need to convert the rotational frequency to revolutions per second. N equals 2200 divided by 60, which is approximately 36.67 revolutions per second. The memo solves this by finding the total angular displacement and then using the work energy formula for rotation. First, we find the angular velocity omega, which is 2pn. Omega equals 2 pi times 36.67, which is approximately 230.47 radians per second. Second, we find the total angular displacement, theta, during the 45 seconds. Since the speed is constant, implied, theta is omega times t. Theta equals 230.47 times 45, which is 10371.15 radians. Third, we calculate the work done. The rotational equivalent of work is W equals T times theta. W equals 40 Newton meters times 10371.15 radians. This gives us approximately 414,846 joules. A more direct method is to first calculate the input power of the machine using P equals 2 pi nt. P equals 2 times P times 36.67 times 40, which is 9222679 watts. Then work done is power times time. W equals 9226.79 times 45, which is 415, 205.55 joules. The memo's answer is 414,837 joules. The small difference comes from how they rounded the value 4 in. They used 3667. The memo's method is acceptable, but it's important to be careful with rounding throughout the process. Now for part C, the output power if the efficiency is 75%. The input power, which is the power generated by the spindle, is 9226.79 watts. Efficiency is the ratio of output power to input power. So, output power equals input power times efficiency. The output power is 9226.79 watts times 0.75, which equals approximately 6920.09 watts. The memo provided a result of 6933.95 watts. The difference is again due to rounding, specifically the memo using 36.667 for, and which results in a slightly lower output power. Both methods and results are fundamentally correct. To recap question 11. We used the torque formula to find the load, calculated the work done in two ways, and then found the output power considering the efficiency. This completes our final problem. That completes activity 2.3. We've worked through 11 problems covering torque, power, angular kinematics, and efficiency in rotational systems. Thank you for joining Math Zone African Motives. We hope this step-by-step tutorial was helpful. Subscribe for more tutorials from Math Zone African Motives.